introduce this year's Welsh Award winner, Eric Jacobson from Harvard University. So it's hard to say a lot that hasn't already been said at this conference about Eric, since we have numerous speakers that know him well, have collaborated with him, and have actually worked with him. But I'll just give a brief introduction of his background for those of you that weren't at the banquet last night. So he did his undergraduate studies at New York University. He then moved to Berkeley for his PhD, working with Bob Bergman, where he sort of gained his incredible skills in physical organic chemistry, mechanistic analysis. He then did a postdoc at MIT with Barry Sharpless, where he studied asymmetric catalysis. Again, you can sort of see where this area in his group was sort of the formative aspects of that. And then moved to University of Illinois, where he started his independent career. And then several years later, moved to Harvard University, where he is now. And so we've heard a lot over the past few days about the impact that he's had on the field of asymmetric catalysis. Eric has made, I think you can look at Scott Miller's list of important reactions as sort of a who's who of important reactions in asymmetric catalysis, sort of delineating new privileged scaffolds for carrying out asymmetric reactions, as well as really fundamental mechanistic aspects of those transformations. And so I thought what I would do is actually talk about some of Eric's scientific impacts that weren't mentioned, which I think are still really profound, because there's lots of areas in chemistry now that are extremely popular, and you'll see lots of research proposals on them as you look at new faculty candidates and things like that, that I think really stem in large part from Eric's seminal studies. So for example, one thing that you'll see lots of people be very interested in is earth-abundant metal catalysis. Eric's original epoxidation catalyst was a manganese complex. The dynamic kinetic resolution chemistry that he developed was cobalt-based catalyst. And so really, obviously there's been many people working in earth-abundant catalysis, but I think that those are some of the really beautiful examples of the power of these first-row metals for doing important transformations. Other examples, I think, as someone who did metalloporphyrin chemistry as a postdoc and appreciate how challenging it is to make metalloporphyrins, if you look at Eric's, epoxidation catalyst, manganese saline epoxidation catalyst, you appreciate immediately how this mimics metalloporphyrins, mimics biology, but yet is incredibly easier to make and really versatile in that regard. And then finally, I think the dynamic kinetic resolution chemistry, where you have these two cobalt catalysts that work together, is a beautiful example of asymmetric catalysis. It's a beautiful example of a powerful chemical transformation, but also this idea of two metals working together to do a reaction as a mechanism that is now sort of, there's lots of people interested in cooperative bimetallic catalysis well beyond what he originally discovered. So I think Eric has had a profound impact on chemistry. I think what you've seen over the past couple of days is that he's had a profound impact on his people. So people that work with him, and you've seen that in the past couple of days. You've seen that in the wonderful video that they had last night, if you were here. He's also impacted people that didn't work for him, and you've heard about that as well. And so I just wanted to give a really brief anecdote. I would just say that when you're applying for jobs, you often get asked kind of strange questions, And so I remember I was at Georgia Tech, and I gave my proposal presentation, and at the end of it, they said, well, in 5 years, people are going to be writing promotion letters for you. If everything goes the best you could possibly imagine, what chemist in the field would you want to be compared to? What person in the field would you want the letter writers to say, this person is, Melanie is as good as this person. And it's kind of a weird question to ask someone, I thought, at least at the job interview, but I did not even have to think for a minute. I said Eric Jacobson. And I would say at the time, that answer was really based on his incredible impact on chemistry. I would say now, if someone asked me that same question, I would say the same thing. But it would be based not just on chemistry, but also the tremendous impact that he's had on people in his group as well. So it is a privilege and an honor to introduce Eric and to welcome Tim to the stage for his Welsh lecture. So let's give him a round of applause.
That was amazing. Thank you. So I was sure you're going to say I'd want to be compared to Eric Jacobson because I would look good by comparison, which would definitely be true in your case, Melanie. So thank you. That was incredibly generous. And as you might imagine, this has been a pretty overwhelming 48 hours for me, and so much has been said. I wasn't sure if I was supposed to give a sort of career retrospective talk or more sort of current results talk. I've ended up trying to do a little bit of both, but I feel a little embarrassed because the quality of the talks and sort of the cutting edge aspects of the talks in the symposium have been incredible. So I want to remind everyone that Melanie arranged this symposium, this whole schedule, except for my talks. So congratulate her on the symposium and don't blame her for some really sort of older stuff, development of ideas, but hopefully that will be interesting to you as I try to take you to where things we're thinking about today in my group. So I'm going to do something really crazy maybe. I'm going to start with a couple of slides that I used to start my sophomore organic chemistry class. And it's things that have been discussed and said already in the symposium, but I think it's so useful to remind ourselves of this. So organic chemistry is useful. It continues to be useful. We tend to emphasize that. It's kind of strange. It's a field that has been useful since the 1870s, or depending on how you count, and continues to this day. So from an economic point of view, and the work that Shane does, and pharmaceutical companies, and materials companies, it's just enormously impactful. And we tend to emphasize that when we communicate to the outside world. When we talk amongst ourselves, we tend to emphasize the fact that organic chemistry is interesting. And certainly when we teach our classes, we tend to emphasize that, maybe even underemphasizing the utility aspect and trying to get across some of these concepts that are so foundational to our field. But I think it's useful to remind ourselves that what we do is really fundamentally incredibly interesting. It frustrates me that physicists seem to be so good at capturing people's imagination with dark matter and exoplanets and things like that that have absolutely no consequence, as far as I can tell, except that it captures the imagination. Yet we're understanding the universe at a molecular level and manipulating it and manipulating structure to achieve function in increasingly rational ways, which unambiguously we'd all agree is the frontier of science, or at least one of them. Yet it's hard for us to communicate that. But we have to keep working at that because what we do is fundamentally incredibly interesting. Okay, so I'm gonna, my sort of background has been described, but I'd like to go over it a little bit. I did my undergraduate work at NYU, I mentioned last night, but I did my PhD work at Berkeley with Bob Bergman. Of course, Bergman needs no introduction. He's one of the great mechanistic chemists of all time, and he had made the transition from physical organic chemistry to organometallic chemistry when I joined his lab. And I was fortunate that my first project worked out pretty well, and he really allowed me to pursue a project of my own design as my next project. And I had become very interested in what was known as the oxymetallocycle hypothesis that had been proposed by Sharpless a few years earlier, which really drew from the metathesis-Chauvin mechanism as a mechanism for how epoxidation and other oxidation pathways might occur in transition metal chemistry. And what was captivating to a budding organometallic chemist was the idea that organometallic intermediates might be involved, the metal-carbon bonds. So I was really fascinated by this, and very much as in the mode of a sort of inorganic organometallic chemist, my thought was to try to synthesize an intermediate that might look like an oxymetallocycle. And where I ended up was a sort of really rational idea of trying to stabilize the oxymetallic cycle by having the carbon attached to a middle to late-ish transition metal, low valent metal that makes strong metal-carbon bonds, and the oxygen to an early transition metal that makes strong metal-oxygen bonds. And that led to this tungsten-zirconium bimetallic complex, which it turns out was kind of unstable and decomposed thermally or photochemically to the metal oxo in alkene. And this might not look that interesting, but from a mechanistic point of view, given the principle of microscopic reversibility, right, this is essentially the opposite of this step. And to me, was incredibly exciting as it's not proof, but certainly support for this oxymetallic cycle hypothesis. So I continued with this interest in this area, which led me to want a postdoc with Sharpless, and I was fortunate to get that opportunity. And of course, again, Barry needs no introduction, but as often the case with postdocs, I was invited to give a talk, a group meeting on my PhD research, and I was excited to do so because I was going to confirm the Sharpless hypothesis, the oxymetallic cycle hypothesis. So I present it, and those of you who know Barry won't be surprised by this. He sort of sat there distracted for a while, and then when he finally looked at it, he said, "That's the worst idea I have ever seen in my life." And his reasoning was that this is a terrible way to oxidize alkenes, and you're never going to do catalysis around sort of trying to stabilize the a key intermediate in the ground state. So what I learned from him, and was sort of humbling, but certainly very valuable, certainly is something he's emphasized throughout his career, this idea of reactivity and good reactions. And he has some favorite sayings, like the Conforth saying at the bottom, really connecting sort of my brain to this idea of practicality in reaction development. So I came out of this experience really with an appreciation, I think, for the connection between fundamental mechanistic thinking, but also practical synthetic application, and with the hope of trying to tie them together. So Sharpless was an incredible inspiration, is an incredible inspiration. His mentorship was a little bit distant because he was on sabbatical a lot and traveling a lot. Really a truly important part of my education was getting to know Steve Buchwald, who was an assistant professor at the time at MIT, and sort of took me, for reasons I'll always be grateful, under his wing and mentored me and inspired me, and I'm sure that I would not have gone into academics if it hadn't been for Steve. So I'm forever grateful, and grateful that we've been friends ever since. Okay, I got the opportunity to start at the University of Illinois, and even though I only spent 5 years there, they were the 5 most important years, scientifically. Certainly, I'm deeply grateful for the time I had there. I mentioned Peter Beek last night, and I'll just mention again, he inspired me in many ways. Those of you who had the chance to know him know what I mean. The younger people in the audience might not have even ever heard of him. So I want to really emphasize what an extraordinary person he was. He sort of demonstrated to me not just the privilege that we have to be able to do science and creative science and work in fields that we love, but also to be a gentle person in doing this, and to be a kind person, and to be generous. And I've really tried to emulate him throughout my life. Okay, so with this interest in practicality and fundamentals, the most inspiring result to me, and what really drew me to the field of asymmetric catalysis, obviously working with Sharpless, but it was really this result, this famous result from the Monsanto and Knowles, the discovery of the reduction of dehydroalanines to make phenylalanines to make L-DOPA, which is hard to overemphasize. You know, again, younger audiences might not appreciate just how extraordinary this was as a fundamental advance and as a practical advance. This changed the way people thought about science. It taught people that small molecule catalysts could do highly enantioselective chemistry. And it also became directly the commercial process for the manufacture of an important medicine. So sort of the ultimate dream of doing practical and fundamental work at the same time and certainly set the bar very high for work in the field of asymmetric catalysis ever since. So with the mindset of a physical organic chemist, what drew me from the start and continues to draw me is this idea that asymmetric catalysis is fundamentally a problem in kinetic control, has to be, because the products are equal in energy thermodynamically. So any enantioselectivity measurement is, in effect, a relative rate measurement. And you can translate very easily the ratios of products to an energy difference. Now, that assumes single pathways, but sort of the aggregate of pathways leading to one product versus the other gives you this key energy difference, which, to achieve high enantioselectivity, we all appreciate, is actually very small, right? So the bad news is that it's very hard to control chemistry at the level of 1 to 2 to 3 kcals per mole rationally. But the good news is, to the extent that we can discover asymmetric catalytic reactions, this is an incredibly powerful mechanistic tool, because it's giving us insight into these transition states at a 1 to 2 to 3 kcal per mole resolution. And if we can understand the basis for those selectivities, we have a way of learning about mechanism at that level of resolution. And that always struck me as an incredibly powerful mechanistic tool, and I think it is. So Melanie mentioned where I started, and the idea was a very simple one. I often think about the fact that when I read proposals from assistant professor applicants, just how impossible the task it is that we present to them to come up with a completely original idea that's likely to work and within a span of 4 to 5 years, and that's totally separated from anything that they've done before. It's ridiculous. And I also appreciate that it's ridiculous, sort of the bar that we set, because it has to be also very creative. The proposal that I had, that I never would have put in my job applications because it was so trivial in a sense, was that metal silane complexes could be, chiral metal silane complexes could be effective for oxotransfer reactions. That was already known that from Kochi's work that you could do epoxidation catalysis with complexes of this type. But sort of the insight was that you have sp3 centers nearer the metal with silane complexes than you do with porphyrins. And people had been doing a lot of work trying to bring stereochemistry or stereochemical elements close to the reaction site with porphyrins. That continues, the work of Peter Zhang and other groups. But this is a much more straightforward way, I thought, to do it. And you could never put that in a proposal. Basically, what I was saying is I was going to take Kochi's work and use chiral diamines to make catalysts from that. It's a too trivial an idea. And in fact, it was a simplistic idea. When we made the first complexes, we saw very low levels of enantioselectivity, essentially none. We had a mechanistic model based on Jay Groves' work that epoxidation occurred by sort of a side-on approach of alkene to a metal oxo. And it became clear that the silane design was flawed in that even though you have stereochemical elements near the metal site, they could be remote from the trajectory of olefin approach. So really the key insight in the epoxidation story was the idea essentially of creating a steric wall around 3/4 of the catalyst to force the chemistry to occur over or near the stereochemical element or the stereochemical communication within the ligand framework to achieve enantioselectivity. So that was really as simple as that idea was. And it worked quite well for certain classes of olefins. Really, it has to be said, quite narrow substrate scope in that only certain classes of styrenyl substrates and other conjugated substrates. But it has some very practical features to it, like the use of hypochlorite as an oxidant, which made it appealing, and also a catalyst that uses an earth-abundant metal and is very easy to make. But there are severe substrate scope limitations to this, which became readily apparent. And quickly I get questions like, oh, can you make propylene oxide, or things like that that were commercially of great interest? And the answer was simply no. But as has been mentioned, what really turned sort of my life around, I guess, in this early stage, was the fact that there was an immediate application of this chemistry in incredibly beautiful work that was done in the process group at Merck, more or less at the same time. The medicinal chemist at Merck had developed this molecule as a medicine for the treatment of AIDS. It's a very complex molecule at the time, sort of almost unprecedentedly complex for something that would have to be synthesized at large scale. And the epoxidation could be incorporated in a straightforward way into that synthesis. And thanks to that, the chemistry got applied in a not just process context, but in a quite large scale context. And again, it's hard for me to sort of wrap my head around just how fortunate I was that this connection was made, because from this sort of fundamental work, this is a slide that John Schwab developed for a presentation to Congress about why they should support basic research. And they connected sort of this epoxidation reaction to the application of an AIDS, synthesis of an AIDS drug. So obviously, an incredible stroke of good fortune for the chemistry, and great reward for seeing the chemistry used. Now, as a physical organic chemist, I was a little bit overwhelmed by that, but actually the result that was perhaps most exciting to me, and maybe is the most impactful in a longer term, was a discovery that we made because we were trying to find ways to isolate the metal oxo intermediate that was involved in this epoxidation chemistry. And we're using sort of classical substituent effects on the ligand to try to stabilize that metal oxo complex. We never succeeded in isolating those complexes, but what we did observe was quite dramatic effect on enantioselectivity with just changing these remote substituents on the catalyst. And those correlated very nicely in sort of a Hammett correlation, where the enantiomer ratio is related to essentially the electronic parameter of those substituents, which at the time was really not something that people thought about, the idea of sort of electronic tuning of enantioselectivity in reactions. So clearly this is not a steric effect. People were thinking very much in steric terms at the time. And we're able to interpret that and sort of support this pretty, I think, compellingly with an argument that what we were doing was tuning the reactivity of the complex, and thereby, through the Hammond postulate, tuning the position of the transition state along the reaction coordinate, with a later transition state leading to a more intimate sort of stereochemical communication in the reaction. But this idea of electronic tuning of enantioselectivity has certainly had a lasting impact and is now one of the fundamental tools, certainly in the field. So as has been mentioned, we later developed kinetic resolution of epoxides that ended up being sort of directly inspired by the epoxidation work, the same ligand, but now with a cobalt center, oxidized under the reaction conditions to the cobalt-3 complex, promotes hydrolysis of epoxides with really pretty remarkable efficiency. Again, I'd been presented with propylene oxide as a challenge for epoxidation. And it was mentioned earlier, propylene oxide in racemic form is one of the major oxidation products of industry. It's actually cheaper than almost any organic solvent in racemic form, but the enantiomerically pure version was actually at the time synthesized in several steps from lactic acid, so there was no practical synthesis. So this route that involves hydrolysis actually becomes appealing because even though it's a resolution, it turned out to be extremely efficient and extremely practical from the point of view of parameters that I came to appreciate, like volumetric throughput and isolation on large scale and things like that. So very rapidly, this chemistry saw practical application. But it also turned out that this chemistry was much broader, much richer in scope than what we had seen earlier in the actual epoxidation reaction. So I've shown this slide, so this is obviously a very old listing, but some of the epoxides that we were able to illustrate this chemistry with, where we get essentially an enantiomerically pure epoxide in close to the quantitative theoretical yield as isolated epoxide. And those that are framed in boxes were those that were scaled up outside of our lab in industrial context, some on extremely large scale. Again, as a physical organic chemist in me, what I'm really most excited about in the hydrolytic kinetic resolution story is what we learned about its mechanism. And as Melanie mentioned, We learned that it's a cooperative bimetallic mechanism. It's actually extremely subtle in its detail, but fundamentally comes down to the catalyst splitting into two different roles, one as a Lewis acid to activate the epoxide, and the other as a counterion to the hydroxide derived from water. So you have activation of the electrophile, activation of the nucleophile in the enantiomer and rate-determining step, ring opening step. Even more remarkable, this balance of roles is established as an equilibrium between the cobalt complexes, depending on the counterion on that cobalt. And this equilibrium is established under the catalytic conditions such that the system by itself essentially achieves optimal reactivity in this dual cooperative role. That cooperative bimetallic mechanism led to the obvious idea of linking the catalysts, finding ways to link them to sort of overcome the entropic cost of cooperativity in an intermolecular sense. And by playing around with this more or less empirically, we ultimately arrived at cyclic oligomeric catalysts, mostly as dimers and a little bit of trimer that are synthesized and used as a mixture, but turn out to be extraordinarily efficient in the epoxide hydrolysis. So these are some examples that I know about that are applied commercially to this day, and really sort of are the most dramatic examples that I've had the opportunity to experience in terms of catalytic efficiency, and certainly the cost of the catalyst drops out entirely from the process cost. The sort of a key fundamental question that's tied to this cooperative mechanism is how is it that this cooperative interaction between two complexes can be both so selective and so accommodating of different substitution patterns on the epoxide. So remind you that the substituent on the terminal epoxide can be varied quite freely. Here are just some examples. These selectivity factors just sort of represent sort of the equivalent of enantioselectivity or enantiomeric ratio, but in terms of the relative rate of reaction of the two enantiomers of epoxide. And what we learned through what was really sort of a almost 20-year study of this reaction mechanism was, I think, a really beautiful picture that you have a sandwich-like transition state between the two cobalt-salient complexes in this ring opening event. And these are DFT models that sort of fit with all sort of the experimental work that we did in this context. But the beauty of this, in my mind at least, is that the model for the opening of propylene oxide and for T-butyl ethylene oxide is almost identical, and they're superimposed in this image. So basically, this catalyst system can achieve the reaction of two sterically very different terminal epoxides by exactly the same mechanism, not just the same arrow pushing mechanism, but the same transition state structure. And of course, that's a sort of a clue into generality, right? Is the catalyst will be general to the extent that it can achieve selectivity through whatever mechanism it needs to do to recognize the exact shape of the epoxide enantiomer, but ignore whatever it is that you want to vary on the substrate without having to fundamentally change its mechanism of recognition. And that's achieved in this case simply by pointing the substituent out and essentially into this open quadrant. Of course, the other element is functional group compatibility. So the added requirement for generality in substrate scope would be you want to ignore what you want to vary in the transition state assembly, and you also want the catalyst system to recognize only the functionality that is going to undergo reaction. And of course, that's a very high bar. It's one that I'll come back to, but it's certainly at the basis of a lot of what we heard about in the talks in the symposium about sort of the quest for generality. What really, I think, was entirely unexpected in this story of the metal-salin chemistry was that this same chiral framework, the identical one, sometimes with some variations to the substituents, but often just in this tetra-T-butyl original variant, turned out to be extremely efficient in enantioselective catalysis of all sorts of different mechanistically unrelated reactions, where the only variation is the identity of the metal, reactive metal center and counterions. So Lewis acid-based mechanisms, more recently radical mechanisms, redox pathways, cooperative pathways, These are mechanistically unrelated processes where the same chiral information somehow is communicating effectively such that high enantiomer selectivity is achievable. And this is sort of what led us to this idea that Teshik and I published on now a couple of decades ago, this idea of privileged catalysts. So in our definition, privilege means specifically this idea of generality beyond what you would ever expect. So catalysts that are effective across a wide range of different mechanistically unrelated contexts. So certainly the premier example of that are the cinchona alkaloids, which are a story unto itself and a fascinating story of how this natural product class turns out to be effective as a ligand, as a salt, and as a nucleophile, and all sorts of other contexts. But there are an increasing number of examples of chiral frameworks that have this feature of generality across different reaction mechanisms. I'm not sure what Steve will talk about this afternoon, but certainly his work in the copper hydride field highlights how privileged ligands can be applied really sort of in incredibly effective ways in entirely new contexts. So the question that I've been fascinated by, my group has really been interested in over the last few years, is what underlies this generality principle, this generality across different reaction mechanisms. How is it that a chiral environment can communicate across a transition state, not just effectively for that transition state or for scope within that transition state for reaction class, but across fundamentally different reaction classes? Now, of course, that's almost a philosophical question, but to me, it's a really interesting physical organic chemistry question, and one that I'll try to answer, at least in some ways, for the rest of this talk. So one obvious way to think about generality is through steric hindrance. So if you have a prochiral flat substrate and you want to achieve phase selectivity with that substrate, block one side of it. Just sterically occlude one side of such that approach is hindered. And in that way, you will get diminishment of reactivity, but the other phase, to the extent that is less hindered, can still undergo reaction, and you'll have high phase selectivity. And this is certainly a really reasonable and effective strategy, and it's one that the field relies on in a large number of cases, and we've relied on certainly in a number of reactions, and illustrated in sort of 4 classic examples here. One that I think will always be important and useful, but it's always struck me that this is entirely different from the way that we think about the catalyst that we've heard about so beautifully from Francis's and Allison's talks of how enzymes operate. That enzymes don't operate by steric hindrance and by blocking trajectories and reducing reaction rates, but rather by selectively stabilizing transition states. So the Pauling hypothesis of selective transition state stabilization through whatever interactions that it takes to bind a transition state more tightly or more favorably relatively than the ground states. This is one of my favorite examples, the enzyme that promotes the Claisen rearrangement of a charismate mutase, and that operates through this network of attractive non-covalent interactions. This is sort of a transition state mimic structure that sort of shows the network of interactions. So the question that we've been very interested in the context of generality is this a reasonable way to think about selectivity and generality in small molecule catalysis? Is it even conceivable? Do you need the large assemblies that exist in enzymes to achieve this sort of network of interactions that will be necessary for transition state stabilization? And what and actually this sort of is a connection for me to the Welsh Foundation, because my other experience at the Welsh in 2009 was the first time that I talked about this work, and the idea or the observation that we had made in some early examples of hydrogen bonding catalysis, that these were reactions that operated through this idea of networks of attractive non-covalent interactions. Hydrogen bonding together with secondary interactions that could selectively stabilize transition states leading to the major enantiomers of product. So to tell this story, and because Matt is here, sort of humbly describe how we really arrived at these hydrogen bond donor catalysts, So Matt Sigmund, when he was in the lab, was interested in the idea of developing libraries, combinatorial libraries, of potential ligands for transition metals or other metals to do asymmetric catalysis. And you can sort of recognize the Salin-like motif in this structure that linked through a urea to an amino acid for added diversity, and then ultimately to a solid support. These are compounds that we can make in parallel and in fairly easy ways. The model reaction was a Strecker reaction shown here, and in a control study, Matt looked at a number of different metal salts to insert into this ligand framework, and fortunately did the control where he left the metal out and found that actually that ligand metal-free molecule was comparably reactive, but actually displayed the most interesting enantioselectivity, albeit very modest in the initial stage. But because of the nature of this compound and its modular structure, could optimize it fairly systematically. And in pretty short order, Matt was able to find that highly enantioselective catalysts can come out of this. So our entry into this idea of hydrogen bond donor catalysis, really have to admit, was initially because ureas are a really good way to link diamines to amino acids through the two nitrogens. But these turned out to be the catalytic engines in not just the Strecker reaction, but it turns out a wide range of other chemistries. So everything that I think you need to know about ureas and other dual hydrogen bond donors in terms of their catalytic properties, I think is represented nicely in these two crystal structures of the same molecule, a bis urea linked through a rigid scaffold, in the absence and presence of an ion. In the absence of an ion, the ureas hydrogen bond to one another in sort of the familiar manner through the carbonyl and the NHs. But if you introduce an anion like chloride, tetraalkyl ammonium chloride, one of the ureas turns around to present its hydrogens and bind the chloride in sort of this 4H binding mode. This interaction is remarkably strong, and of course it's been studied in molecular recognition and in ion transport and all sorts of contexts. But we came to appreciate that this could be a really powerful concept for catalysis. And the idea in the simplest form could be one more simple promotion of SN1 pathways, where an anion binder, a dual hydrogen bond donor, could either abstract or bind a leaving group from an organic molecule to generate an ion pair within a catalyst framework. Now, coulombic attraction is quite strong in organic solvents, but it's very non-directional. So that simple ion pairing is not nearly enough to achieve any sort of enantioselectivity in subsequent reactions. But thought is that if we have secondary elements to this structure that could orient and stabilize this ion pair, you could conceive of achieving enantioselectivity. And this idea turns out to be a very powerful one, this idea of anion binding catalysis, in a sense, not just in the context of SN1 pathways, but in all sorts of pathways that involve either ion pairs, acid co-catalysis, or transition metal co-catalysis, or non-ionic pathways wherein anion abstraction is achieved cooperatively with nucleophile activation in various types of ways to achieve sort of stereospecific substitution pathways. But all of these really requiring sort of cooperativity between the anion binding hydrogen bond donor motif and the secondary features of the catalyst. So in the context of this kind of effort, we've arrived at a few different classes of chiral hydrogen bond donors that have this catalytic engine, the sort of the urea or thiourea or sometimes squaramides. These are all sort of comparable, and we don't really fully understand which will be best in a given context. But dual hydrogen bond donors that are then linked covalently in very simple structures to secondary elements that can promote sort of these attractive interactions. Now, Scott presented really beautiful examples of squaramides with strong base components, secondary components. And that's a really exciting field of sort of strong base or more or less strong base cooperativity with hydrogen bond donors. And we've certainly been involved in that arena. But what you'll notice about these structures is that there isn't really functionality that you would recognize as sort of traditional reactive functionality. These are sort of even the sulfonamine, which is really quite weakly Lewis basic, but these other elements really just have sort of polarizable structural motifs that flank the hydrogen bond donor. So I'm just going to talk about one story that illustrates the application of these catalysts. And this is a story that I think took some interesting turns and has led us to an interesting place, I'd say. So this is work that was done by Dan Strassfeld and Zach Wickens when they were in the lab, and was directed to opening the enantioselective opening of 3 substituted oxetanes. So this is sort of a second distant cousin of epoxide ring opening, but actually quite powerful transformation from a synthetic point of view, giving us these difunctional 3-carbon building blocks. So they found that this particular squaramide bearing this aryl prolidine was highly effective for a number of different 3 substituted oxetanes, and quite efficient as well. So from a synthetic point of view, this was quite an attractive reaction. There actually turned out to be an opportunity to use this chemistry in a large-scale process, which led us to do sort of a deep dive mechanistic analysis on it, which led us to observe that we were having some serious reproducibility problems in this reaction. Not so much in terms of enantioselectivity, but in terms of rate. And it was something that took us a while to sort out, but what we learned was that the mechanism that we had sort of anticipated around this, that the hydrogen bond donor could effectively split TMS bromide into an ion pair that can then sort of rebound and open the activated oxetane, that pathway was in competition with a second pathway that existed if there was any adventitious proton source, which is not hard to get with TMS bromide. So any HBr that's present turns on a different pathway that is similar in its general features, again involves splitting of now this Bronsted acid to an ion pair that undergoes ring opening. But it turns out the bromohydrin product undergoes silylation under the catalytic conditions to return the same product as in the TMS bromide pathway. So it is not unusual for a given catalyst to give the same product by different mechanisms. Karen Goldberg gave a great example of that in the O2 insertion into metal hydrides yesterday. But what was strange to us about this was the fact that both of these pathways turn out to be highly enantioselective. And we could isolate those pathways under sort of non-catalytic conditions to show that both the sort of HBr pathway and TMS bromide pathway with the same catalyst were highly enantioselective. So it's hard to explain, if you're not in this field, why this was sort of such a rattling result, because sort of there's a premise in asymmetric catalysis that it's really hard to achieve high enantioselectivity. And if you do, it must mean that it's proceeding by a single mechanism. You can't have a bunch of competing mechanisms leading to the same product, because it's hard enough to get high enantioselectivity in one pathway. You're very unlikely to get it in multiple competing pathways. Now, that said, if you've ever done a DFT calculation on an enantioselective reaction, you see a whole distribution of transition states that lead to enantiomers. That's not strange, but this is a different reaction. It's not different transition states, it's different reactants in the catalytic site. So we did it really, well, Dan in particular, Dan Strassfeld did a deep analysis of how it might be that this catalyst can communicate so effectively across these two different ring opening transition states, the proteo and silyl-activated oxetanes. These are electrostatic potential maps of the catalyst and its reactive conformation. The conformation is very similar for the two pathways as calculated. And then the transition states that fit within that active site, which we've pulled out effectively as electrostatic potential maps. And what you see in these pictures is that these expectedly have quite different shapes, but as it turns out, very similar polarization in the transition state. Meanwhile, the catalyst also has sort of very dramatic polarization. You have the hydrogen bond donor site, which of course will bind negative charges, and then the electron-rich aromatic and group and amide, which are potentially the cation binding sites. But I love this picture because it really sort of looks like a very handed, or even a hand or mitten, dipolar active site. set to accommodate dipolar transition states. And the idea that sort of struck us from this is that we might be achieving this kind of generality because fundamentally what this is privileged catalysis, right? This idea of high enantioselectivity across different mechanisms with the same catalyst. This is it in one system. How is it achieving this generality? Well, it's not by recognizing the specific shape of the transition state, but rather recognizing the polar features of that transition state within a specific chiral environment. And that strikes me as a very generalizable principle, right? Think of all the polar mechanisms in organic chemistry. If we can sort of accommodate the polar transition states in those mechanisms with a polar or dipolar catalyst framework that is asymmetric enough to really differentiate the energies of the two enantiomeric pathways, we should be able to do a lot of polar chemistry around that. In a simple extension, we've looked at azetidines bearing different nitrogen substituents and found that indeed the same catalyst under very similar conditions can, again, promote highly enantioselective ring openings. And again, what you see in these maps is really dramatically different steric features, but similar dipolar features in these transition states that can be fit into the catalyst. So the key idea here is not sort of totally revolutionary, certainly, but it's the idea that by using transition state stabilization rather than transition state destabilization to promote enantioselectivity, if you stabilize sort of a common feature of transition states, you can achieve generality with a lot of freedom around what steric and even functional features you have in the reaction. So we do the normal thing. We're writing this up now. Joe Gayer and Mayuko Isomura developed the azetidine project, and there's really nice scope to this chemistry in that we can do 3 arrow substituted azetidines and then some quite interesting other types of substituents. But as is often the case in these types of exercises, there are also quite striking limitations. So small alkyl substituents and unsaturated substituents fare quite poorly. This is completely normal. This is actually what I would consider, in my experience, a really good substrate scope, so nothing to be ashamed of. The only question is, do we hide these results deep in the SI, or do we put it in the main text? Do we discuss the limitations? And here, really, we get to the issue of generality that has come up in so many of the talks in the symposium. There was a practical matter in that it turned out that this was one of the targets that we're most interested in. This is a really interesting building block for some synthetic applications of pharmaceutical compounds. So we were actually interested in this. But the fundamental point here was that we had used the phenyl substituted derivative as our model substrate in this optimization. And sure enough, we optimized for that and then saw good results, not just for similar substrates, actually remarkably quite different ones. But there's no reason in the world to expect that these substrates that are so fundamentally different from our model should be effective. And this gets to my final point, which has been articulated so nicely in various points in the symposium, this idea of thinking about generality in selective catalysis. What we do, and I think what's historically been done throughout the history of the field of asymmetric catalysis, is that you pick a model substrate and the reaction you want it to undergo, and then you do your optimization. How you pick that model substrate could depend on maybe a specific application for a target, but more often than not, it's the most vanilla, easiest substrate you can come up with because you don't want to miss anything, right? So you pick an easy substrate, and then you optimize. And if you're successful, right, optimize around catalysts and other space within the optimization sphere. And if you're successful, you find a highly, in our case, enantioselective system. And then, and only then, do you consider the scope of that reaction. So then, as you say, we hope or we pray that there is good substrate scope to that reaction. And needless to say, the reactions that tend to be the most impactful are the ones that have broad scope, because they can be used predictively in new contexts. But there's no reason why you should expect that scope from this approach. And as Frances has articulated, I don't think she came up with this phrase, maybe she did, but certainly It's a truism now that you get what you screen for. You screen for a specific substrate, you will get conditions that work for a specific substrate. So the answer is so obvious. The answer is that we should screen for generality. If generality is important and connected to utility, we should screen for that. And this is something that we've thought about in the group for years. Eugene Kwan, who's quite well known now in the field and is very successful at Merck. And I thought about this since he was at Harvard. And the question that we were sort of came to terms with is that the problem to a significant extent is a technical one. Why we don't screen for generality, because I've been asking my group to do this for forever, and they simply say, Eric, you have not been in the lab for a long time, you don't know, is that it's sort of tedious and hard and time-consuming to assay products, especially in an anti-selectivity context. So the idea that we developed, Corin Wagon, who was an extraordinary student who came from Steve's lab, and Eugene and Spencer at Merck, is the idea of using, instead of using spectrophotometry as a detection method for EE analysis, as is typically done, where you really have to purify your compounds and separate them to get resolution of enantiomers, that we could use mass detection together with efficient chromatography. This is a trace of 20 different racemates where they just happen to have different masses. This is retention time. This is a 4-minute run on SFC. And even though they overlap, certainly in their elution, they can be analyzed separately simply by a selective mass detection. So the idea that's exciting to us is the idea that we can run reactions in parallel, but then pool the products as crude product mixtures and analyze them in very efficient ways and get enormous amounts of EE data that way. The only thing that we have to be careful about is, obviously, we need separation conditions for each of the products, so the right column, and they have to have different masses. But this has enabled us to generate data sets like this. And I realize this is an awful slide in terms of the actual data, but the intention here is simply to show that dark green is high in enantioselectivity, white is low in enantioselectivity. That we can generate data sets that are much richer, that involve examining a series of catalysts across a series of substrates simultaneously or in the same operation, almost as easily as we would do around a single model substrate by our traditional approach. In this way, Mayuko Isomura, in collaboration with Merck and Eugene's group, did that kind of analysis on the azetidine opening. And I'm just going to distill it down to one result, but I think it's an exciting one and a telling one. So on the left was our catalyst we had originally identified, and identified around the 3-phenyl azetidine. On the right is a catalyst that she identified from the screening for generality approach, which turns out to be non-optimal for the original model substrate, but turns out much more general and evenly effective across different azetidines, including the ones that were most problematic with the original catalyst. So effectively, by screening for generality, she identified a much more general catalyst, one that we obviously missed in our initial effort, because in the initial effort, 3-phenyl just happens to not do as well as the original catalyst. So it seems straightforward, and again, there's all sorts of different ways that people are thinking about the screening for generality approach, but I'm hoping that the generation of data sets like this that I hope are high enough quality that we can use both the good data and the bad data to feed into the types of models that Abby and Matt discussed yesterday, and be really informative for, ideally even for prediction purposes. But that can also lead us to results that would have been very difficult to find otherwise, unless we happen to be lucky enough to pick the right single model substrate. To the physical organic chemist in me, what's most exciting maybe is that this is giving us mechanistic information that we tended not to get before. And this is deeper analysis of, or at least information that's the basis for analysis of pathways that lead to both high enantioselectivity and loss of enantioselectivity. Instead of what typically we've done is optimize, pick the best substrate, and study that system and get the DFT model for that and understand what underlies its selectivity. Now with this broader data collection, what we have are examples of high selectivity, but also selectivity where you break the selectivity. So this is simply distillation where we've done DFT calculations with these two catalysts and these two substrates. Obviously, we've expanded this way beyond this, but where we're able to get very good agreement between the models and the experimental data. And of course, this is giving us insight into changes in mechanism effectively as a function of different catalysts and different substrates, which again, I think is going to be so crucial for thinking about generality. What is actually happening here, I'll just show in this final slide, and that's this thiourea catalyst. Notice that we've changed the identity of the hydrogen bond donor. That's actually not so much the key feature here. It's a combination of that with a change in the arylproline that leads to a fairly significant change in the conformation secondary structure of the catalyst and its ability to bind substrates and recognize substrates. Fundamentally, what the catalyst on the left does is to recognize that aryl group or other sort of polar group at the 3 position, whereas the catalyst on the right is much better at sort of just recognizing the azidine transition state itself and not specifically recognizing the 3 substituent. So it's better suited for generality. Okay, that's where I'd like to end. And I don't know if I have an answer to this question that I posed earlier, what underlies sort of this privileged nature of certain catalysts, but I think there's probably almost certainly multiple answers to this question. Steric hindrance will always be a powerful device in catalyst design, but I think if you're using steric hindrance and transition state destabilization, then you really have to think in terms of rigidity. You cannot have a flexible catalyst that inhibits all competing pathways but one. It has to rigidly accommodate that transition state, and that's certainly a useful design principle. But if you're using transition state stabilization as a selectivity principle, then flexibility really is your friend. The catalyst to adapt to different substrates and different reactions, perhaps, to achieve that type of transition state stabilization. So one of the professional joys and personal joys I have is Scott Miller and I have regular Zoom calls where we talk about everything, including the role of flexibility in catalyst design and transition state stabilization. We're working on a review that should come out in around 2035, I think, at the pace we're doing it. And I'm excited about that, but this is certainly an idea that has become a very powerful one in the field. Scott and I laugh about sort of seeing proposals from starting people where people say, I've got this, the flexibility is sort of the obvious design principle, and non-covalent interactions are the obvious design principle in asymmetric catalysis. And we're happy to see that, but it certainly didn't start out that way. So we're grateful, I'm grateful for everything surrounding this, but certainly to the direction that this chemistry has taken. Okay, I have abused my time. I'd like to thank my current group. So we take a yearly trip to Gloucester and take a picture on the beach. So this is the most recent picture with Virginia in the picture, and Mayuko, who's just left, and Gabriel Lovinger, who's also just left. He's at Purdue, and Mayuko's going to Illinois. I'm grateful to them. You saw a lot of pictures of me in the group yesterday. You're probably sick of me. I'm getting sick of me by now, but I just wanted to show this picture, which wasn't shown yesterday. So this is from a birthday symposium that was 10 years prior to the one that was mentioned yesterday, that Abby organized. It's actually a surprise party, Abby with Izzat Rahim. And it was an incredible event, but it's a picture that doesn't do justice to my most recent students, but is special to me because both Barry Sharpless, sorry, my lasers died, but you'll find him sort of middle left, and my undergraduate advisor, York Rhodes, attended, as well as an incredible number of my former students. You see Abby in the front left, and Matt Sigmund sort of in the middle. The amazing thing is Matt wasn't even giving a talk, but he still came, as did many other people, because we enjoy each other's company. So I have eternal gratitude to my group. Thanks again to the Welsh Foundation for the honor, and thank you so much for your attention.
So thank you, Eric, for an incredible lecture. In the interest of time, I think we're going to break for lunch and reconvene at 1 o'clock. And anyone that wants to come up and talk to Eric, ask him a question, take a picture, this is your opportunity. So please do that. Yeah. And we'll see you back here at 1 o'clock.